the winner. Okay, so you're given an integer array nums. Two players are playing a game with this array, player 1 and player 2. Player 1 and player 2 take turns with player 1 starting first. Both players start the game with a score of 0. Okay, at each turn, the player takes one of the numbers from either the end of the array or from the beginning of the array. Okay, so you can take an element from either end, and that'll be added to your score. The player adds the chosen number to their score. The game ends when there are no more elements in the array. Return true if player 1 can win the game. If the scores of both players are equal, then player 1 is still the winner. You should also return true. You may assume that both players are playing optimally. Okay, so if we look at this example, 152, is it possible for us as player 1 to win if we're playing an optimal opponent? Well, we can either choose 1 and the opponent will be given 5-2, right? Or we can choose 2 and the opponent will be given 1-5. Okay, or 1-5. Yeah, 1-5. All right, so let's go down this rabbit hole. So we choose 1, the opponent's given 5-2. Well, the opponent's also trying to win, so obviously the better thing for the opponent would be to choose 5, which will then present you with only 2, and you'll notice that you lose this game because you chose 2 and 1, and the opponent chose 5. So you've lost this version of the game. On the other hand, if you choose 2, well, then the opponent again is obviously going to choose 5, right? Because 5 is more optimal. Right? It's a higher value. If he's only given 1 or 5 to choose from, he's obviously going to choose 5 optimally. And then you will have to choose 1, and you lose again, 3-5. Which is why the output here is false. So I think a natural algorithm to approach this problem with is Minimax tree, right? So the idea of a Minimax tree is to go through the turns of a game. So we'll have this function called turns. And it's a zero-sum game, right? Because whatever the player, if you imagine that all the possible points you could get is the sum of this array, right? The total number of points you can get is 8, right? 1 plus 5 plus 2, 8. It's a zero-sum game because if I gain one of those points, the other player doesn't get that point, so he loses a point, right? If I get 5, he doesn't get 5. So if you think of something as a score, well, we can think of the score as I'm trying to maximize the score that's received, and the opposing player is trying to minimize the score, right? Another way you could look at this is saying, well, when we looked at the example of 152, right? I ended up with 3, and the opponent ended up with 5. But all that really matters is that the opponent has more points than me, right? So we could say that's a difference of -2, right? 3 minus 5. My score minus his score is -2. So if the ending score is negative, that means the opposing player has won, right? Or on the other hand, if the ending score is non-negative, right, greater than or equal to 0, that means I won. So instead of keeping track of how many points I have and how many points the opponent has, we can just keep track of what's the difference between the two scores at any time, right? And at the end, if the difference of the score is negative, that means the opposing player won. And if the difference of the score is non-negative, greater than 0, or greater than or equal to 0, that means that this player won. So we can run through each turn that way. And we can look at places in the array that we could be, right? Because like if we thought of I, J as being positions in the array, right? The game starts out like this. And if I play with an I starts here and J starts here, if I decide to select 1, that would mean that the opposing player is given the array like this, where I is here and J is here, right? And then if the opposing player chose 5, then that would mean that I'd be given the array where I is here, I put 1, weird, where I is here as well as J. So the idea is that instead of having to like present this person with a new array, we can just keep these pointers to keep track of where we are in the game, right? What this indicates here is that I chose 1, so I move the pointer over to the right ones, right? This indicates that if this is chosen, that means that I chose, right? If you're given this, that means whoever's player turn it was before it got to the state, right? So whoever's turn it was here, right? If it goes from here to here, that means that they chose 2, which is why J is here. So just an easier way of, so you have a turn, which is a state, right? You have an array that you're given where certain elements have been chosen, and then you have whoever's turn it is, right? So we'll just call that player, I guess. Right. So the idea here is, well, remember, this notion of min-max tree is like, I'm trying to maximize the score, right, to get it as positive as possible, because we're talking about the difference here. We're talking about the difference of the score, which is this idea that I'm trying to maximize the difference, because a positive difference means I'm winning the game, right? That I've won the game. And a negative difference means that the opponent's won the game, right? If I end up with 3 points and he ends up with 5 points, then he won because the difference is -2. So he's going to try to get that value to be as negative as possible. So you can think of any scores being, if there's +3, that means I got +3. And if there's -5, that means that he got +5. But the difference would make it -2. Okay. So I think I've exhausted articulating that point at this moment. So let's just go through with this solution. So first thing we say is, well, if I is greater than j, that doesn't really make sense, right? Because I is always the pointer on the left that's increasing, and j is always the pointer on the right that's decreasing. So maybe we call this left pointer and right pointer, right? The left pointer is going more to the right, the right pointer is going more to the left. So the left pointer should always be to the left of the right pointer. So if they're not, then that means that you've used the whole system, right? So you just return 0. No one else can get any of the points. If it's the player's turn, right? If it's my turn, I'm trying to maximize my score, right? Now, what are the two things I can choose? Well, I can choose nums at I, but that means then that I have to give, okay, I called it I and j because I'm just so used to using those. So if I choose the element at the left, that means I have to present the user, right? If nums is 1, or if nums is 1, 5, 2, 3, 4, right? If I choose left here, say that the array was currently at this state here. If I choose 5, that means that I need to increase L by 1, and then the user's given LR like this, right? So if I choose L, I have to increase L by 1, and then it's not my turn anymore, right? So it's not the player's turn anymore. So that's the first thing I can do. Or I can choose the element at the right pointer, and I have to decrease it by 1. So L is the same, but now I decrease R, and again, it's still not my turn. Otherwise, it's not my turn, it's the opponent's turn, and his goal is to minimize the difference, so he's going to try to minimize the score. So he gets, so it's very similar, so I'm just going to copy this verbatim. So he gets a minimum score. He gets negative nums points, right? Because he's trying to minimize this difference if he uses the left or the right. And again, it's not his turn, so this will just oscillate, right? This will flip the binary value of this variable at every iteration of this recursive stack. And then we'll just erase this. And then we'll run to see if this works. So, well, this works, but it's not. It's false positive here. So we have to return, if we run this game with L is 0, right? Because that's the first element of the array. And R is going to be the length of the array -1, so it's the last index of the array. And it starts off as our turn, right? Because the player goes first. I put turn here. It's true. So it's going to fail. 3, 2, 1. Okay. I forgot in Python the capital T. All right, so let's refresh and run this again. Of course, it takes forever to load when you're trying to make a video. Okay. Num is not defined. Did you mean sum? Nums, num. Inaccurate archetype for. Okay, so I just said max here. Okay, so we got to return that, right? Because that's the solution. Sorry. That's why I'm so bad at contests, the sloppy little mistakes. Okay, so this is saying true. So what's going on here? If it's my turn, take the maximum of choosing the left element and increasing by 1, or taking the right element and decreasing r by 1. Otherwise, it's the other person's turn, and they're going to get the minimum of taking the left element. Okay, so return this is greater than or equal to 0, right? Because I win if I start and the result of the difference is greater than or equal to 0. Not just that it exists. So we'll submit this, and I'm just going to quickly state that this is going to give a time limit exceeded error, because we're going to get a lot of repetitive values, right? Because we're going to end up being in states where we shouldn't have been before, right? This runtime is atrocious. So we can run this again, and I'm guessing that it won't pass. This is kind of on the very edge of what's accepted. So to kind of speed up this solution without thinking deeply about the recurrence relationship between the variables is to add a catch which remembers states that we've been in before, so that we don't reuse information, right? So what we can do instead is, this is recursion with memoization, right? This is usually the preferable dynamic programming approach when you don't fully comprehend the recurrence relationship. It can be more difficult in these kind of situations to determine, right, your runtime and your space complexity, but this is better than nothing if you can't determine the recurrence relationship, right? Just try something and see if you can work in a catch to remember information. Okay, so we'll look at each state. So if L, R, and player is in state, well, then we can just return that. Otherwise, we can set the state here and here, and then we return that state. So just by adding, one line, 2 lines really, we added this line, we added 2 lines, and we modified 3, right? We're going to see a huge improvement in runtime. Of course, this is going to slow down, this is going to add additional space, right? Because we have to save information about each iteration of this system, but it's going to save us from having to continue to compute the same thing. Okay, so what's the runtime of this? Well, for each state, we create 2 additional states, but notice that we only have to look at states for each LR and player pair. So how many LR player pairs can be? Well, player can be 0 or 1, right? So there's 2 things. So the runtime of this is going to be confined by the size of this system, right? Because there's a quantifiable, right? There's a countable size to the number of situations that you could be in, right? There's a finite number of LR player pairs, so we can determine the runtime of the system by just exhausting, well, how many possible LR player pairs can we find? Well, for player, it's in a system of either being 0 or 1, right? L can be anything from 0 to the length of the loop, or the length of nums. So it could be the length of nums, and I'll use the same interval notation to articulate that, nums minus 1, but this is, of course, and then same thing for R, right, but going the other direction. So because R can be length of nums minus 1, and it can move all the way down to 0. So the whole number of states is, well, there can be 0, 1 times L times R. So 0, 1, so that's 2 options per player. There's length of num options for nums. So we'll just call n equals the length of nums times n, and then another n here. So that's 2 times n squared. And then in terms of big O time complexity, we're looking at n squared time complexity. And then, of course, this is based on the catch, right? So the catch and is determined by the size of the number of iterations of this loop. So this thing could run n squared times, right? You can continue going down this recursive stack n squared times, but also the catch that you can create can have at most n squared values. So this is n squared time complexity, and n squared space complexity. Now, one note before I finish this video, like 99% of the time, if you can do something with recursion memoization, you can also use it with the recurrence relationship via dynamic programming. But I'm not actually 100% sure what the recurrence relationship is in this problem. I'm going to think about that after I finish this video. But it's a little tricky, right? Because, well, what's the relationships of these states, right? Like you have player's turn and not player's turn, but you also have this notion of like how many points you have and where I and J are, right? Because right, L can increase by 1 or R can decrease by 1. So trying to think about what the recurrence relationship is. I'll think about that though. All right, thank you guys. Have a good day. Night.